Welcome back to section 5 of chapter 0. In this section, we are going to be looking at inverse functions and logarithms. And those go together because, as we'll see, a logarithm is the inverse of an exponential function that we just saw a couple chapters ago, or sections. First of all, our learning targets for the day. I can determine whether functions are one-to-one. That is really just more of a definition type question. I can determine whether functions have inverses. I can find inverse functions. That's one of the big pieces of this one. I can use parametric graphing to graph functions and their inverses. I know we just got done with parametric functions and it's a little bit traumatic. Finding an inverse of a parametric function is remarkably easy. I can't wait to show you that. And I can solve exponential and logarithmic functions. We looked at exponential functions a few sections ago, but we weren't able to solve them because we needed logarithms. So now we'll be able to solve them. Happy day. All right, so inverses. What is an inverse? An inverse is where the input and the output of a function switch places. A great example of inverse functions would be the formula to go from degrees Celsius to degrees Fahrenheit. The inverse takes it from degrees Fahrenheit back to degrees Celsius. So it switches the order, it switches the input and the output. The first thing we're going to look at is one-to-one functions. How is a function one-to-one? Well, a one-to-one function means both it and its inverse are functions. So we know that when we're checking to see if something is a function, we do the vertical line test. That tells us that each x value has exactly one y value. In order for it to be one-to-one, each y value also has to have a unique x value. So if you know the x, then you know the y, and if you know the y, you know that specific x. To test that, we use the horizontal line test. So something like a quadratic, a parabola, might be a function because it passes the vertical line test, but it does not pass the horizontal line test. So it is not one-to-one. And what that tells us is its inverse is not a function. That doesn't mean it doesn't have an inverse. It means that its inverse is not a function. So what could work? A cubic function could work as long as it doesn't have any big loops in it. Or not loops, but like the humps where it goes up and then back down, then back up again. So this would be one-to-one. It is a function, and its inverse will also be a function. Inverses, as I mentioned, is where we switch the input and the output. To do that, we switch the x and the y. And that's all it is. If we are looking at a table, we just flip the columns on the table. So if we have a table that has x and y, the inverse would simply be x and y. The numbers would be the same. We just switch which one's x, which one's y. And testing to see if something is an inverse, f of x and g of x are inverses if we get a composite function. F, that's g, well, g of f of x equals f of g of x, which equals x. So if you take a composite function, one of the other, and it simplifies down to x, then they're inverses. That does not tell us how to find an inverse though. So how do we find an inverse? In order to find an inverse, we literally switch the x and the y. So if we have, say, f of x equals 3x plus 7, first thing I would do is change that to a y equals 3x plus 7, and then we literally switch the x and the y. X equals 3y plus 7. Now we solve for y again. So we're going to subtract 7 and then divide by 3. So y equals x minus 7 over 3. Put it back in function notation. The notation for inverse function, f to the negative 1 of x, means the inverse of f of x. That's what the negative 1 exponent means. The 2 to the negative 1 is the multiplicative inverse of 2. So that's the general way we would do this. If we had something like the Celsius Fahrenheit, if we had like that formula, C equals blah, blah, blah with F, just solve it so it's F equals blah, blah, blah with C. Don't switch the variables, because then all of a sudden the meanings are completely weird. That's finding inverses using the Cartesian coordinates, but I promise to tell you how to find inverses parametrically as well. So to do this, if we have a parametric equation, let's say x equals 3t, y equals sine t, remember, to find inverses, we literally switch the x and the y. So the inverse is x equals sine t, y equals 3t. Is that not beautiful? So easy. The parameter may change a little bit, but you just flip it around. That's all it is. Which brings us to logarithms. Like, what a logarithm? What is that? Well, I said it's the inverse of an exponential function. Remember, an exponential function, we have something like y equals, say, b to the x. A logarithm is the inverse. It uses a word, the word log, but what it is log is x equals log base b of y. So it takes that exponent and it moves it out to the front. Now, the b has to be a positive number, not equal to 1, just like this. The y is going to be positive because y is positive. Like, we're not going to get b to a power and get a negative number out of that. That's going to be a positive number, so y is going to also be positive. The x could be positive or negative, however. And so what we can do with this is we can actually rewrite exponential and logarithmic equations. So if we say something like 2 to the x equals 8, well, we could rewrite that as log base 2 of 8 equals x. And you could go back and forth with that. The logs have some properties, just like the exponential ones do. We have a product rule. If you have the log of two things being multiplied, you can split that up with addition. Log of x plus log of y. So now I'm not putting a base on this. That means that the base is just base 10. It's called the standard base. The base is going to be the same for all of these. That's not going to change. Regardless of what the base is, it'll just stay the same. I'm not going base B because that just adds one extra variable into the mix. Quotient rule, kind of same idea. Log of x over y. Well, if we added when we multiplied, we're going to subtract when we divide. And a power rule, log of x to the y. This is a useful one. What this one says is we can actually take the y and move it out front. Y equals log of x. You guys have seen these properties before. This is just a review of what they are, because sometimes they get a little bit forgotten. We have a change of base formula as well. This is a good one because our calculators can do base 10 and they can do base e, which is the natural log, but they can't do other bases. So to change the base, if we have log base a of x, we can just change it to our new base. I'm going to use the natural log, which is ln. That is ln, not in. Natural log of x over natural log of the old base. So the natural log, I'll put x, is defined to be the log base e of x. Remember, e is the natural number, that 2.718 number. So we can change the base. That way, if we had, say, log base 5 of 17, we could do log 17 over log 5, either base 10 or natural log 17 over natural log 5 in base e. And that allows us to figure those numbers out. And so how would we use this? Went into my space here. I'm going to erase some of that. We've seen that. You can rewind if you need to see it again. How could we use this? Well, if we have an equation, we can use logarithms to solve for t. The first thing we need to do, or to solve for the exponent, we need to get the base to the power by itself. So we're going to divide by 1000, which gives us 1.0525 to the t equals 2.5. And the next step is we're going to take the log of both sides. I'm going to take the natural log because that's the one I usually take. Sometimes it doesn't matter. Sometimes the standard log is easier, but most of the time, if something's going to be easier, it's the natural log. So I always take natural log. As we proceed through calculus, you will find out why e is my second favorite irrational number and why the natural log is so amazingly fantastic. But I would take the natural log. And so, using our exponent property here, that t can come out in front. So we have t times the natural log of 1.0525, which is just a number. And that'll equal the natural log of 2.5, which is also just a number. So we can divide natural log of 1.0525, natural log 1.0525. So we get t equals, and this calculation you would do in your calculator. I would type in natural log 2.5, enter, get that decimal. Now the very next button I would push is natural log. Do not clear it out and retype it. You push natural log, it's going to say, hey, my previous answer, which was the numerator, divided by natural log, then type in the 1.0525. Writing it down, retyping the number is, first of all, it's less efficient, so it's way less lazy, and we don't want to do that. Second, the calculator keeps more digits than it shows you, so it'll be more accurate if you keep it in there, and you're going to risk making a mistake, and you don't want to round it until the very end as much as you can. So leave it all in the calculator. Let the calculator do that for you. When you calculate it out, it should come out to be about 17.9. And so that's how we can use logarithms to solve those exponential equations. And so that was our quick review on inverse functions and logarithms. I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.